Welcome to this webinar about multi-core functional safety applications. My name is Christopher Seidel and I'm your host today. Today's guest speakers are Marcelo Williams from Infineon and my colleague Milorad Cvjetkovic, who will run the demo. Today, we'll start with a quick overview of functional safety in embedded systems. Then, Marcelo moves on to an introduction to Infineon's TRAVEO 2 devices, which are designed for functional safety applications. After that, Milorad shows you a live demo with a traffic light example on a 3-core system. We'll finish with some useful resources you can take away, and of course, a Q&A session at the end. Before we start, let me highlight the past webinars that offer deep technical insights into various aspects of embedded development. The first episode featured an overview over Keil MDK, explaining all the components and the different editions. The functional safety components that we're talking about today are part of the MDK Professional Edition. The second episode introduced you to the MDK middleware. The third episode went into further detail about dual-core debugging. We can only touch that aspect today, so if you are interested, please view this episode. The SDS episode was about gathering real-world data for ML applications and how to play them back to virtual and real hardware for testing purposes. You can review these sessions anytime by accessing these links. Let's look at a modern embedded application running on ARM Cortex-M devices. These processors are powerful and development is often accelerated by using building blocks from different sources, an RTOS, a C library, HAL and drivers from the device vendor, middleware like comms and graphics, maybe even an STL for diagnostics, all tied together by the application itself. But in safety systems, this gets tricky. Safety-critical software must follow strict processes, the V-model, detailed analysis, extensive validation, and heavy documentation. For smaller OEMs, this can be technically difficult and not economical. So how do we address this? We can't change the standards, but we can reduce the scope of what needs full certification. One way is to use certified components. For example, Arm FuSa RTS already provides a certified RTOS, C library, and part of the HAL, saving significant effort in the core system. Other components may also have certified variants, though they can be costly. And often, with smart system partitioning, we don't even need certified variants. By isolating safety-critical functions from lower integrity ones, a mixed criticality system, we can meet safety goals efficiently. And this is exactly where Arm FuSa RTS helps, as we'll explore later in this webinar. Safety-critical systems demand rigorous verification and compliance with industry standards. To support this, Arm introduced the FuSa Runtime System, or FuSa RTS. FuSa RTS is a set of safety-certified software components for use in automotive, industrial, medical, and railway applications, all certified by TÜV Süd to the highest integrity levels. The certified components include Keil RTX RTOS, long proven, now safety certified with features like static and dynamic memory allocation. FuSa Event Recorder, which captures kernel activity, user events and timing data, which is essential for integration testing. The FuSa CMSIS Core, which is a certified runtime layer for Cortex-M, giving direct access to the processor core. And the FuSa C library, a subset of ISO C99 functions with guidelines and examples for safe usage. FuSa RTS is delivered together with the safety-qualified ARM Compiler 6, providing a fully certified development toolchain for your applications. Some elements remain outside certification scope, like device-specific CMSIS core parts and the software test library, but these are minimal and straightforward to verify. In short, FuSa RTS gives you a ready-made, certified foundation, so you can focus on safety efforts where they matter most, your application. Functional safety standards require us to prove two things. First, that software is developed at the right ASIL level, and second, that components don't interfere with each other. That's tough in single-core systems where mixed safety levels share the same processor. FuSa RTS solves this with process isolation, giving us freedom from interference. It works in 3 ways: spatial isolation with MPU-protected zones and safety classes, temporal isolation with watchdogs to enforce timing, and controlled recovery to keep the system safe in case of failures. In short, process isolation lets safety-critical and non-safety functions run together, reliably, securely, and in compliance with functional safety standards. Now, I hand over to Marcelo Williams, who will tell us more about Infineon's FuSa certified controller portfolio and especially the TRAVEO 2 series. Marcelo, the stage is yours.
Hi, Christopher. Thanks for the insights, what ARM and Infineon can do together with our microcontrollers. First of all, I want to go over our product portfolio here. What you can find here is what we are offering our website. You have basically two sets of microcontrollers, which are the automotive or functional safety ones, and we have the consumer industrial in the bottom of the page. What we'll be talking today is the microcontrollers from transportation and automotive functional safety, which includes the PSOC, our Cortex M0 devices, which can be a multi-touch or fingerprint, very application-specific ones. We have the Multics, which is M0 and M3 for motor control integrated devices. We have PSOC 4 general purpose. We have the PSOC HV, which is the high voltage up to 42 volts. We have the TRAVEO, which is the main topic of today. It's a Cortex M4 or M7 up to quad-core M7. Very interesting device. We'll discuss later about all the capabilities. And also we have our tri-core devices, call it RX. So going one level deeper on the TRAVEO devices, basically we have three families. The TRAVEO body device are general purpose microcontroller, which we have the body entry, which are Cortex M4 devices, and we have the body high, which is Cortex M7, starting with single core up to quad core. And then we have the TRAVEO T2G graphics or cluster devices, and these ones, the peripherals are exactly the same of the body, but we do offer the graphic capabilities on a microcontroller. Very interesting devices, very good to use. So they are all Cortex-based, ultra low power. The top devices, they have KNFD and gigabit Ethernet. You have the Vita Full for cryptographic portion. You have the true firmware over the air. You have up to ACLB, and this will be the scope of this webinar here, that we'll be discussing how we can explore more the FuSa applications with ARM and all the compliance and AUTOSAR capabilities on those devices. So then talking about the family of the TRAVEO body devices, today, as I mentioned here, is exploring a bit more what are the CPUs, the capabilities, and the size of flash and RAM. And we do offer the TRAVEO T2G body high, which are the Cortex M7 from single M7 to dual core and quad core M7s, with more capabilities like the Ethernet, the gigabit Ethernet, the KNFD, all topics that we mentioned previously. What will be new here is that Infineon is still investing in this family. We still have lots of new devices coming. So guys, please stay tuned that we will have the TRAVEO body extension family here, which will be higher performance with lower footprint of flash memory and more connectivity capabilities. But stay tuned that we'll be bringing on along the year in other webinars the functionalities of the TRAVEO body extension. So going one level deeper on the diagram block of the TRAVEO devices, here you can see a superset of the TRAVEO body high family with 8 megabytes. This one, dual core M7. So what you see here across the whole family of the TRAVEO is that they follow the same peripherals and the same structure, so it makes easier for you to migrate from one family to the other ones. So we have all the system control here combined. You have the core block with all the MPU and the PPU portion, especially for the FuSa applications. Pretty cool feature. And you have the dual core M7 can be single core M4, single core M7, dual core M7, or quad core M7. We do have the cryptographic engine here with another Cortex M0. So if you're not using the Cortex M0 portion, you can use this as a secondary microcontroller in your application. Then you have all the peripherals, including the motor control PWMs, smart GPIO, so all the things that turns TRAVEO as kind of unique to this application, plus one main feature that is the 2.7 volts to 5.5 volts across the whole product portfolio from M4s to M7 to double M7s, so you don't need to spend extra money in LDOs or 3.3 LDOs outside. So what will be your key takeaways from this presentation? It's that TRAVEO family multi-core combination, so you can go from a single M4 to a single M7, dual M7, or quad M7. Same applying to the cluster devices. You have low power consumption of down to 35 microamps in deep sleep mode with run retention. So you can have peripheral and run retention even on ultra low power consumption, kind of unique thing for TRAVEO. You have the wide voltage of inputs that I just mentioned, 2.7 to 5.5 in all product family. You have the true firmware over the air, so you can read without together with writings, and you have different blocks of memory that you can make your software much simple using the true firmware over the air. You have the pin-to-pin compatibility across the whole family. As I mentioned previously, you have the HSM that can be used as a second microcontroller if you are not using the cryptographic part. And last but not least, these types of memory of protection units, which is inside this application notes, the MPU, the MPU, and the PPU, they are provided following the structure from ARM. So it makes the software much more easier to use and in a very structured way, as Christopher will be explaining right after this session. Okay, thank you very much.
Thank you, Marcelo, for sharing this with us. As we just learned, some of the TRAVEO T2G devices have 3 processor cores. In our application, the Cortex M0 Plus core is used to bootstrap the other 2 cores. The second Cortex M7 core just blinks an LED to show that it is free for other purposes. The traffic light controller application runs on the first Cortex M7 core. It cycles through the standard phases red, red-yellow, green, yellow, with the green time adjusted based on traffic load. This demo showcases the process isolation in FuSa RTS, protecting components with different safety levels from interfering with each other. Normal operation runs at a lower safety level. Its behavior is constantly monitored, and if something goes wrong, control shifts to a higher integrity safe mode, where only the yellow light blinks. A TCP/IP interface handles user input and provides status updates via a web browser. If faults occur in lower-level functions, only those threads are suspended. The rest of the system, like communication, continues. But if a higher-level fault occurs, everything below is shut down and the system falls back to safe mode. This way, FuSa RTS ensures the system always remains in a safe state, no matter where the fault happens. The example is available in this repository. Let's take a look at it. This is the repository. You will get the link to it at the end with the handouts, so no need to write it down. And we have in the README a quick start guide that explains how to use the example in the repository. Milorad will show that later in the demo. Important to understand is that you can run the example with the MDK Community Edition, so you don't need MDK Professional or the FuSa RTS. We are using the plain vanilla Keil RTX, which offers the same functional safety features, just without the certification. Here we detail a little bit more about the app, so the 3 different projects for the Cortex M0 Plus and the 2 M7s. We're using different MPU zones. The TRAVEO T2G series devices have even further or more sophisticated MPUs that we're not using in this example, but I encourage you to check out the datasheet of the devices. And the repo also has a test and a driver validation project, because we had to add CMSIS drivers for Ethernet for our MDK middleware that does the web hosting of the application. So we added them to this repo. And of course, we also need to test them. This is in this project available. Some words about the Git workflow, how you can use this with GitHub Actions, for example, and also in continuous integration and hardware in the loop tests. So one example in here is you can run this on a Raspberry Pi, for example, and then check the results on the development board connected to that Pi. This, of course, does not replace sophisticated hill systems like from some of our partners, for example, Protoss. But you can use that for printf debugging, which is absolutely fine. And we will add more features to PyOCD as we are working on it. Little more info about the files and directories, and we will of course also post the webinar here. So this is all you need to get started, so please take a look. Now I hand over to my colleague Milorad, who will demo the application.
Thank you, Christopher. Hello, my name is Milorad Cvetkovic, and I'm a member of Arm's Keil embedded development team. I will demonstrate traffic light safety application running on the Infineon TRAVEO T2G BH light board using Visual Studio Code for development and debugging. Let's start first by cloning this GitHub repository to our local machine and go from there. So first, let's clone it. Let's select the repository destination. Wait for it, and okay. We can take a look into this now. VC package file. This is a file that describes all the necessary tools, and we can see here under ARM tools that tools are being installed. This will happen only the first time that tools are not yet available. Once they are first time installed, that it will not be triggered again when the next time the project is opened. After the tools have been installed, we can also check the pack installation. So it will continue with installing the required packs, the packs that are required by this solution. And we'll wait for this to finish. This repository contains multiple solutions, and we can select the active one by selecting the CMSIS view and selecting active solution here. So this one has two. We'll use the first one as the one containing the traffic light example. First, we have here board and device. Basically, those contain links to the board documentation and device documentation. After that, we have three projects, which are actually projects for three different CPUs that are on this device. Boot one is used for booting the device. It runs on Cortex M0 Plus, and it just starts the other two cores. On the first M7 core, Cortex M7 core, we will be running the traffic light example, and on the second Cortex M7 core, we will be running just a Blinky to show that they are separately running independently from each other. In the managed solution, we can see basically these three projects, and they are currently all selected because we need to download them and run all of them to be able to show this example. Let's now go through the traffic light example in a little more detail. The README file contains application structure and operation description. Let's go now through the code itself. So safety class 0 contains two modules for normal operation and operation verification. We'll see that later how it looks like on the real example. Then we have safety class 1, which is higher safety class, meaning it has a higher safety integrity level than the previous one. This one is used for the web user interface. Then the next one, the highest one, is one for the safe operation. This one is just blinking the LED light, and it signals that the device has entered the specific mode and that normal operation is no longer functional. Under system, we have basic application, and we have faults module, which we'll take a look in a little bit more detail. So these are all the handlers for the different errors and faults that can occur in this application. And they have a deterministic way of handling it. For example, for a watchdog alarm, we have specified the way that it's going to be handled for a specific threat. Then we have also components, which are generic SMSIS components. And then we have a board layer, which has board-specific drivers and components. For example, under board, we have MAC and PHY driver. Then we have retargeting, which is used to retarget standard input-output to the UART on this device. And we have also VIO SMSIS driver, which is used for LEDs and buttons on this board. Let's take a look into the board traffic lights. So these are traffic light specific modules for this particular hardware. For example, this module is hardware specific functionality of a hardware watchdog on this device. And also very important file to show here is, for example, this zone file. This file contains zones, and each zone specifies MPU settings that specify for this particular zone access rights. For example, zone a normal operation, which contains a thread for normal operation, will be able to access flash, for example, in read-only mode, and it will also be able to access shared RAM and event recorder RAM, RAM for normal operation, and also GPIO ports for LED operation. Let's also take a look into the components. So for components, we have here a startup component, which is device specific and is used for this particular case for this Cortex M7 core, first core. Then we have some different specific peripheral drivers, and one of the important thing here is actually this one, and this one is device configurator, which actually allows us to start the Infineon's device configurator. So we can here, for example, see that we can select different peripherals, we can configure them, we can configure pins, we can then also configure clocks. We can also here additional peripheral clocks configure, and the DMA. After we have done the changes, basically, and close this tool, it will actually write out these files, or it will overwrite the files in a way that basically they are updated with the configurations which have been changed in the device configurator. We can also add clang information to have a better IntelliSense experience like so. So you can see now additional IntelliSense information here. Now I actually am going to build all of the three projects, and let's first do that. Now it has finished. I will now connect the development board to my USB. And we can see also here in the target information that actually the board has been connected to my computer. And now we actually are going to start a debug session. So we will download applications to the flash and start a debug session. Now here in the debug and run and debug, we can select which core we want to attach to. So if we want to debug a specific core, in this example, so this traffic light is running on the Cortex-M7 first core, so we are going to attach to this one. And now we are attached, and basically the board is running our three applications: the boot, the blinky, and the traffic light. Let's first take a look into the README here. So README, it specifies here that the web page user interface is actually accessible via this name. So we can do that here. So we can see it here. And this is the web user interface of this application. We can see here the operating mode, which is actually turning on and off the lights as a normal traffic light. We can see traffic sensor, which is simulated or it's changed via the user button on the board. Like pressing it, it goes into one direction, pressing it goes into another. And the point of this sensor is actually, depending on the sensor value, the green light lengthens the duration. We can see here additionally the fault injection part, which is used to trigger different type of faults and actually see the behavior regarding the implementation in the traffic light example itself. I will now actually double click on the user button to see that we are going to enter so-called safe state, and that yellow LED will continue blinking, as we can see here in this user interface. And web user interface is still active because only the normal operation thread was suspended. So we can still see the status from the application itself. And with this, we conclude the traffic light safety application demonstration. Thank you very much.
Thank you, Milorad, for this impressive demo. Milorad was not able to show all the features of our tools. Here's an overview how it works. You can either start with the SMSIS C solution project, or currently we're working on expanding this also to Zephyr projects, so West build projects. And basically PyOCD, our debugger backend, uses the output of the SMSIS toolbox workflow, so the elf-dwarf files, and the cbuild run YAML file, which contains the run and debug configuration information. And then you can use that either in the IDE, as Milorad has shown, or on the command line. So everything is available on the command line. Thus, you can use it in CI/CD workflows. And in our GitHub repository, we have a demo for that. So please explore it. You can use the Keil MDK Community Edition for that, which is free for evaluation purpose. So you can easily review everything we have shown today. Here are some useful resources and further information about our functional safety offering. Remember, all these components we have talked about today are available with MDK Professional. Talk to your distributor or check our developer store to learn about your purchasing options. We are now at the end of the webinar, which I hope you found interesting and useful. I now open the floor for your questions.